Namaste everyone and welcome back to our channel. I am your Java guide and today we are diving deep into one of Java's most fundamental and powerful data structures, the HashMap. You use it all the time, but have you ever wondered how it actually works internally? Well, in this 5-minute animated whiteboard tutorial, we are going to demystify Java HashMap internals, making it super clear and easy to understand. We will cover key-value pairs, the magic of hashing, how buckets store your data, and what happens when collisions occur. By the end of this video, you will have a solid foundational understanding that will boost your Java programming skills. So, grab your virtual notebooks and let's get started. Alright, let's begin with the core idea behind a hash map, storing data as key-value pairs. Imagine you have a dictionary. The word is your key, and its definition is your value. In Java, a hash map works similarly. When you put a key-value pair into a hash map, the very first step is to calculate a unique identifier for your key. This is done using the keys hashcode method. Every Java object has this method, and it returns an integer. This integer, the hashcode, is crucial because it helps the hash map quickly determine where to store your data. Think of it like assigning a unique locker number based on your name. The hashcode method is the first step in this fascinating process, guiding your data to its correct location within the HashMap's internal structure. It is the backbone of efficient data retrieval and storage. Now, once the hashcode method provides an integer, the HashMap uses this hashcode to find a specific spot, which we call a bucket. Internally, a HashMap is essentially an array of these buckets. The hashcode is converted into an array index, pointing to one of these buckets. But what happens if two different keys produce the same hashcode, or if their hashcodes map to the same bucket index? This is called a collision. Java's HashMap is smart, it handles collisions gracefully. Initially, if multiple entries map to the same bucket, they are stored in a linked list within this bucket. Each node in this linked list holds a key-value pair. When searching, if the hashcodes match, the HashMap then uses the equals method to compare the keys within that linked list until it finds the exact match. For larger linked lists, Java 8 introduced a clever optimization. If a bucket's linked list becomes too long, it transforms into a balanced tree, specifically a red-black tree, to maintain performance. This ensures that even with many collisions, retrieval remains efficient. Let us put all this theory into practice with a simple Java code example. Here, we are creating a hash map to store student IDs as keys and their names as values. First, we declare HashMap integer, string student records is equal to new HashMap. Then, we use the put method studentRecords.put 101 alias. Internally, the integer 101 as hashcode is calculated, leading to a bucket where alias is stored. When we call studentRecords.get 101, the hashcode of 101 is again calculated, leading directly to the correct bucket. If there is a linked list, it traverses it, using equals to confirm 101 is indeed the key. Similarly, contains key and remove methods also leverage this same internal hashing and bucket mechanism for their efficient operations. This example clearly shows how these internal workings translate into practical, efficient code. While hash maps are incredibly powerful, there are a couple of common mistakes beginners often make. The first major mistake is using mutable objects as keys without properly overriding hashcode and equals methods. If you modify a key object after putting it into the hash map, its hash code might change, making it impossible to retrieve the value later. Always use immutable objects like string or integer as keys, or ensure your custom key classes correctly implement hashcode and equals and are designed to be immutable once placed in the hash map. Another mistake is forgetting about the importance of initial capacity and load factor. A poorly chosen initial capacity can lead to frequent resizing, which is an expensive operation. Remember, hashcode and equals are a pair. If you override one, you must override the other to ensure correct hashmap behavior and prevent unexpected bugs. Paying attention to these details will make your hashmap usage much more robust and performant. And that brings us to the end of our deep dive into Java HashMap internals. We started by understanding that hashmaps store data in key-value pairs, using the hashcode method to quickly determine where to place or find an entry. We then explored how these hashcodes lead to buckets, which are essentially array indices. We also learned about collision handling, where multiple entries in a bucket are managed using linked lists, which can upgrade to balanced trees for optimal performance, leveraging the equals method for precise key matching. Finally, we looked at a practical example and discussed common pitfalls like using mutable keys and the importance of correctly overriding hashcode and equals methods. Understanding these internals empowers you to write more efficient and bug-free Java applications. Keep practicing, keep exploring, and remember to like this video, share it with your friends, and subscribe to our channel for more Java tutorials. Happy coding, and I will see you in the next video.